Tonight, we're going to look at a photograph that has quietly misled almost everyone who has ever seen it. You've probably encountered it. The Hubble Extreme Deep Field, a single patch of sky, smaller than a grain of sand held at arm's length, containing roughly 10,000 galaxies packed so tightly together that they appear shoulder to shoulder, a glittering, crowded metropolis stretching from one edge of the frame to the other. It looks, at a glance, like proof that the universe is teeming, dense, practically overflowing with galactic neighbours. Here's what most people don't realise. That image is one of the most convincing optical illusions in the history of science. The galaxies in that photograph are not sitting beside one another. They are not neighbours, or anything close to it. They are scattered along a single, almost incomprehensibly long line of sight, stretching from our own cosmic backyard all the way out to the very edge of what light has ever managed to show us. Some of that light left its source less than 5 billion years ago. Some of it has been travelling for more than 9 billion years, arriving from a moment when the universe was less than 5% of its current age. The image isn't a crowded street. It's a hallway seen end-on, with every door along its length photographed at once and flattened into a single frame. The first surprise is that the universe's real architecture is defined not by the matter scattered across it, but by the almost unimaginable emptiness that separates every piece of that matter from every other piece. The second surprise is a genuine paradox hiding in the mathematics of scale. A paradox that makes stars, individually, some of the most isolated objects imaginable, while making galaxies, as a category, strangely and unexpectedly close to one another. The third surprise is a single region of space so profoundly, catastrophically empty that a civilization unlucky enough to evolve inside it might never have known other galaxies existed at all. Not until it had already invented a telescope powerful enough to see almost to the edge of everything. And the fourth surprise is what all of this means for the future. That the distances separating galaxies are not simply large. They are actively, permanently growing, and the night sky you can see tonight is measurably more crowded than any sky any future civilization will ever be able to look up and see again. By the end of tonight, you're going to understand exactly how empty the space between galaxies actually is, why the crowded photographs lie to you, and why the true distance between galaxies is worse, far worse, than almost anyone assumes. Before we dive in, if you're someone who finds real comfort in understanding the true scale of the place we live in, who trades the noise of the day for a little cosmic perspective before sleep, consider liking this video or subscribing to the channel. It's a small thing, but it helps us keep making this kind of content for people who share that same quiet curiosity. Now, let's begin. Human intuition was never built for this. Our sense of distance, our sense of scale, our entire inherited toolkit for judging how far away something is and how crowded a space feels, evolved on a single planet, across distances measured in footsteps and horizons, not gigaparsecs. That evolutionary mismatch is bad enough on its own, but it's made significantly worse by the very tool we use to try to overcome it, astronomical photography. A photograph is, by its nature, a flattening. It takes a three-dimensional universe, stretching in every direction across billions of light years, and compresses it down onto a two-dimensional screen or page. Nothing about that compression preserves depth, and nowhere is this more dramatically illustrated than in the most famous deep field images ever captured. The Hubble Ultra Deep Field, and its successor, the Hubble Extreme Deep Field, universally known as the XDF. The XDF shows a patch of sky so small that it represents roughly 1/32 millionth of the total sky, a sliver so narrow that, held at arm's length, it would be comparable to the apparent size of a single grain of sand. Astronomers pointed Hubble at this one tiny, apparently empty patch of darkness and left the shutter open, collecting light patiently for the equivalent of over 2 million seconds of total exposure time, spread across more than a decade of observations. What developed when all of that painstakingly gathered light was finally combined was not emptiness. It was approximately 10,000 individual galaxies, filling the frame almost completely, packed so closely together in the final image that many of them appear to be touching. This is where the illusion takes hold. Because the human visual cortex has no innate mechanism for judging depth from a static photograph of unfamiliar objects, the brain does something it always does when faced with ambiguous spatial information. It defaults to the simplest interpretation. Objects that appear close together in the frame are assumed to be close together in space. A galaxy in the foreground, sitting beside a galaxy in the background, reads to the human eye as two neighbours sharing a street. They are nothing of the sort. In the nearest layer of the XDF, the galaxies we see are ones whose light has travelled for less than 5 billion years to reach us. In the intermediate depths of the same image, the light has been travelling for 5 to 9 billion years. And at the very furthest extreme, galaxies that, in the flattened photograph, might sit directly adjacent to foreground galaxies just a few pixels away. The light has been crossing the void for more than 9 billion years, representing objects that existed when the universe was less than 5% of its current age, more than 95% of the way back to the Big Bang itself. Two galaxies that appear to be touching in that photograph might, in physical reality, be separated not by a short walk, but by a gulf of space so vast that the light connecting them to us left their respective surfaces at moments separated by billions of years of cosmic history. The image is not a map of a crowded room. It is a cross-section of time itself, sliced along a single line of sight and laid flat. Science fiction compounds this error relentlessly. Spacecraft in movies weave between galaxies like cars changing lanes on a crowded highway. Popular documentaries narrate the galactic neighborhood with a casualness that implies walking distance. The cumulative effect, across a lifetime of exposure to these images and these stories, is a deeply internalized, almost unshakable sense that the universe is full, that matter is the default and emptiness is the exception. The truth runs in the opposite direction entirely. To understand the real architecture of the cosmos, we first have to unlearn the crowded metropolis the XDF seems to show us and replace it with something considerably stranger, a universe defined, overwhelmingly, by the staggering nothing that fills nearly all of it. Before we go further into the darkness between galaxies, it's worth pausing on a genuine paradox. One that even people who accept the mostly empty framing of the universe rarely have fully explained to them. Astronomers have a useful tool for measuring how crowded any given region of space actually is, the ratio between the distance separating two objects and the physical diameter of those objects themselves. It's a simple idea. If two objects are enormous and only modestly far apart relative to their own size, that region is crowded. If two objects are tiny and separated by a gulf many, many times larger than either one, that region is close to empty. Apply this ratio to stars within a single galaxy, and the result is almost dizzying. A typical star is roughly 1 million kilometers across. The nearest neighboring star systems, even in a relatively dense galactic disk like our own, tend to sit several light years away, tens of trillions of kilometers of separation. Divide that distance by the star's own diameter, and the resulting ratio lands somewhere in the tens of millions. Stars, in other words, are not crowded together at all. They are more like individual grains of sand, each one separated from its nearest neighbour by literal miles of nothing. This is precisely why, when two entire galaxies collide and pass through one another, an event that sounds, on its face, catastrophically violent, the stars inside them almost never actually strike each other. They simply slip past, guided by shifting gravitational tides, each one moving through a space so overwhelmingly empty that a direct stellar collision is, statistically, close to negligible. Now apply that exact same ratio to galaxies themselves, rather than to the stars inside them, and something genuinely strange happens. The Milky Way has a diameter of roughly 100,000 light-years. Its nearest large neighbour, the Andromeda Galaxy, sits approximately 2.5 million light-years away. Divide that distance by the Milky Way's own diameter, and the resulting ratio is a mere 25. 25. Not tens of millions. 25. This is the paradox worth sitting with. Individual stars within a galaxy are separated from each other by a factor of tens of millions relative to their own size. Genuinely, overwhelmingly isolated. But galaxies, relative to their own enormous size, sit only about 25 diameters apart from their nearest large neighbor. Relative to the objects themselves, galaxies are, in a strange and counterintuitive sense, close. This isn't a minor mathematical curiosity. It's the entire reason galaxies behave the way they do across cosmic time. Because that distance to diameter ratio is so much smaller for galaxies than for stars, galaxies interact gravitationally on a routine, essentially continuous basis. They distort each other's shapes. They strip long tidal tails of gas and dust away from one another. They collide, merge, and gradually reshape each other's entire structure across billions of years, all while the stars inside them, individually, almost never touch. The universe holds two entirely different truths simultaneously. Its fundamental stellar building blocks live in near-total isolation from their own neighbors, while the grand galactic structures those stars assemble into are, relatively speaking, packed closely enough to constantly, physically reshape one another. So, which is it? Close or empty? The honest answer is both, depending entirely on which scale you're standing at. And once you actually translate that close ratio of 25 back into real, human-relatable numbers, actual light years, actual travel times, you're about to discover that even this relatively tight cosmic relationship is far more isolating than the number 25 makes it sound. Let's step across the threshold from interstellar space, the space between stars within our own galaxy, into intergalactic space, and start with the region we understand best, the local group. This is a gravitationally bound collection of roughly 54 known galaxies, anchored by two true giants, our own Milky Way and the Andromeda Galaxy. Andromeda, as we've already established, sits approximately 2.5 million light-years away, a figure astronomers also express as roughly 800 kiloparsecs. Unlike almost every other galaxy in the observable universe, which is being carried away from us by the relentless expansion of space itself, Andromeda is close enough that mutual gravity has taken over entirely. It is currently falling inward toward the Milky Way at approximately 110 kilometers per second, on a slow collision course that will conclude in a merger roughly 4.5 billion years from now, eventually producing a single, massive elliptical galaxy. Filling the vast 2.5 million light-year gulf between these two spiral giants is a scattered retinue of considerably smaller dwarf galaxies, a kind of population census of the local intergalactic terrain. Our own Milky Way is orbited by satellites of its own, most famously the Large and Small Magellanic Clouds, sitting roughly 160,000 and 200,000 light-years away respectively. Farther out, a scattered array of dwarf spheroidal and dwarf irregular galaxies mark the true depth of our local neighborhood. The Sagittarius dwarf spheroidal, orbiting at about 85,000 light-years from our galactic core. Barnard's Galaxy, drifting in the open space between the Milky Way and Andromeda at roughly 1.6 million light-years. The Sagittarius dwarf irregular galaxy, sitting at the very edge of what astronomers call the local volume, approximately 3.4 million light-years out. And then, beyond even these local boundaries, the universe plunges into a darkness considerably more severe than anything we've discussed so far. Approximately 10 million light-years away sits a dwarf galaxy called KK 246, a small, unremarkable-looking object, except for one genuinely startling fact about its surroundings. There is absolutely nothing within 10 million light-years of KK 246 in any direction. No neighboring galaxy, no dwarf companion, nothing. It sits at the edge of a dark, empty expanse extending outward for roughly another 250 million light-years before the next meaningful concentration of galaxies begins. Let's actually feel the scale of even the comparatively close distances we started with, because the number 2.5 million light-years slides past most listeners without leaving much of a mark. If a hypothetical traveller left the Milky Way today, moving at the speed of light, the absolute maximum velocity the universe permits, the fastest anything can ever travel, the journey to Andromeda would still take 2.5 million years to complete. Not 2.5 million miles. Not 2.5 million hours. 2.5 million years at the fastest speed physics will ever allow. Here's what that actually means in human terms. The light currently arriving at Earth from Andromeda, the same faint smudge you could, in principle, find with your own naked eye on a sufficiently dark night, left its source at a moment when the earliest ancestors of modern humans were only just beginning to use crude stone tools. Every human being who has ever lived, every civilization, every war, every book, every technology our species has ever produced. All of it happened during the time this one beam of light was crossing the gap to our nearest large galactic neighbour. This is shocking discovery number one. Even the close distances in our own cosmic backyard, the 25 diameters apart neighbourliness we just established mathematically, translate into gulfs of space so vast that light itself, the fastest thing that exists, needs 2.5 million years just to cross the shortest meaningful hop between two major galaxies. And Andromeda is the near one, the nearby, gravitationally bound, eventually merging one. Everything else in the universe sits considerably farther away. Pull the perspective back further, past the local group entirely, and the architecture of the universe begins to reveal itself at a genuinely different order of magnitude. The local group, for all its local significance to us, is merely a small, outlying appendage on the outskirts of something far larger. The Virgo Cluster, a massive conglomeration of well over 1,000 galaxies, sitting approximately 54 million light-years away. The Virgo Cluster is, in turn, simply the gravitational heart of the Virgo supercluster, which is itself just one lobe of an even more staggering structure called the Laniakea supercluster, spanning roughly 520 million light-years and containing the combined mass of some 100,000 galaxies. Our entire local group, Milky Way included, is simply one small neighbourhood within this vastly larger structure. To properly map structures at this scale, cosmologists define something called the observable universe, the total spherical volume of space defined by how far light has had time to travel since the Big Bang, which occurred approximately 13.787 billion years ago. And here is where most people's intuition, however carefully calibrated by everything we've covered so far tonight, runs directly into a genuinely counterintuitive wall. The natural assumption, given a 13.787 billion-year-old universe, is that the observable universe should have a radius of roughly 13.8 billion light-years. Light travelling outward from the Big Bang for that entire span of time, in every direction, defining a sphere of exactly that size. Instead, the actual current radius, accounting for the continuous expansion of space during that entire multi-billion-year journey, comes out to approximately 46.5 billion light-years, not 13.8 billion, 46.5 billion, more than 3 times larger than simple intuition would predict. The reason traces back to something we need to understand carefully. While a photon has been travelling toward us for, say, 10 billion years, the space it has been crossing has not been sitting still. It has been actively stretching the entire time, continuously, in every direction. The distant matter that originally emitted the very earliest light we can now detect has, in the time since, been carried outward by that same stretching to a present-day distance far greater than the simple light travel distance would suggest. The observable universe, as a result, constitutes a sphere with a genuinely staggering diameter of 93 billion light-years, a circumference stretching for roughly 292.2 billion light-years, encompassing a total volume of approximately 4.1 times 10 to the 32nd power cubic light-years. There's one more layer of structure worth understanding before we go deeper into the emptiness itself. Beyond a scale of roughly 200 megaparsecs, about 650 million light-years, the universe reaches what observational cosmologists call the end of greatness. At this immense scale, the universe finally appears roughly homogeneous and isotropic, statistically the same in every direction, with an even, unremarkable distribution of matter. But below that 200 megaparsec threshold, everywhere we've actually been discussing tonight, from the local group up through Laniakea, the universe is anything but uniform. It's deeply textured, intricately structured, built, as we're about to see, around a shape that looks less like a random scattering of galaxies and considerably more like an enormous, three-dimensional sponge. The large-scale structure of the universe is not random. It's organized, patterned, in fact, with a coherence that traces directly back to the very first fractions of a second after the universe itself began. When the universe was born, the distribution of matter within it was remarkably, almost perfectly uniform, but not quite perfectly. Microscopic quantum fluctuations in the primordial plasma, tiny, essentially random variations at the smallest conceivable scale, created regions that were ever so slightly denser than their surroundings. Slightly denser meant slightly more gravity, and slightly more gravity, given billions of years to act, meant those regions would eventually win a long, slow competition against the emptier regions around them. Through the combined action of baryon acoustic oscillations, literal sound waves propagating through the hot, early plasma of the infant universe, and the overwhelming gravitational dominance of cold, dark matter, these barely overdense regions gradually collapsed inward on themselves across billions of years, steadily pulling in surrounding material from the less dense regions nearby. The result of this slow gravitational sorting was matter clumping together into immense, thread-like formations called filaments, while the regions left behind, drained of their material, expanded outward into vast, increasingly empty spaces. Galaxies flow along these invisible filaments the way water droplets cling to and travel along strands of a spider's web. Where multiple filaments intersect, they form massive nodes. The dense galaxy clusters and superclusters, like Virgo and Laniakea, where gravitational pull reaches its most concentrated and powerful. These filaments are, without serious competition, the largest physical structures that exist anywhere in the known universe, individually stretching up to 250 million light-years from end to end, forming a glowing, three-dimensional lattice draped across the entire 93 billion light-year diameter of everything we can observe. But here is the detail that matters most for tonight's story. The most profound feature of this cosmic web isn't the glowing filaments themselves. It's the dark, silent expanses that lie between them. Picture the physical structure of ordinary soap foam. What actually defines its shape isn't the thin films of soap, but the pockets of air trapped and enclosed within them. The architecture of the entire universe works precisely the same way. It is fundamentally defined by its voids. The vast regions where matter, for whatever reason, simply failed to accumulate at all. If filaments are the scaffolding of the universe, cosmic voids are the staggering chasms of emptiness they enclose. And while a typical void averages around 100 megaparsecs in diameter, already an almost incomprehensible span of empty space, the universe hosts a handful of anomalous, terrifyingly underdense regions known in the scientific literature as supervoids. The most prominent and most rigorously studied of these is the Botez Void, colloquially and accurately nicknamed the Great Nothing. It was discovered in 1981 by astronomer Robert Kirshner and his colleagues during a survey of galactic redshifts specifically designed to map the large-scale structure of the universe. It sits in the direction of the Botez constellation, its center located approximately 700 million light-years from Earth. The scale of it genuinely pushes the limits of astronomical comprehension. The Botez void has a radius of 62 megaparsecs, a total physical diameter of approximately 330 million light-years across. To put that in perspective, using a number we've already established tonight, the Milky Way and Andromeda sit 2.5 million light-years apart. You could fit 132 separate Milky Way to Andromeda distances, laid end-to-end, across the diameter of this single void. Its total volume comes out to roughly 236,000 cubic megaparsecs, making it one of the single largest continuous empty regions anywhere in the visible universe. Here is the number that should genuinely stop you. Based on the universe's standard average density, a volume of space as large as the Botez void should mathematically contain approximately 2,000 galaxies. Exhaustive astronomical surveys conducted repeatedly over decades have found a total of 60 galaxies in a volume that should hold 2,000. The density of galaxies inside the Botez void registers at less than 10% of the normal cosmic average for a region of its size, and this profound emptiness doesn't conflict with our standard cosmological models at all. Researchers hypothesize that the Botez void formed through the gradual coalescence of several smaller voids, merging together over billions of years and pushing whatever matter remained outward into the surrounding cosmic web. This merger hypothesis is strongly supported by the specific arrangement of the 60 known galaxies that do exist inside it. Not scattered randomly throughout the volume, but distributed in a roughly cylindrical, tube-shaped region running through the void's center, theorized to be the remnant filament boundary of the smaller voids before they fully merged into one. And here is the thought experiment that this level of emptiness makes possible, and it's worth sitting with directly. If a civilization's home galaxy had, by chance, formed in the dead center of the Botez void, rather than in a modestly populated region like the Virgo supercluster, that civilization would likely not have known that other galaxies existed at all. Not until it had independently developed deep sky telescope technology roughly equivalent to what humanity achieved in the 1960s. Their night sky, generation after generation, would have shown them nothing but their own galaxy's stars and a profound, unbroken dark. The isolation would have been, for all practical purposes, virtually absolute. This is shocking discovery number 2, and it's worth letting settle. The universe contains regions so profoundly, structurally empty, that intelligent life evolving inside them could have spent their entire civilization's early history. Every early astronomer, every early telescope, centuries of careful observation, looking up at a sky that offered no evidence whatsoever that anything else existed beyond their own galaxy's boundary. Cosmic voids like Botez represent extreme, localized emptiness. But here's the detail that should genuinely reframe everything we've discussed so far tonight. The average density of the entire universe, everywhere, including the busiest, most galaxy-rich regions, is still shockingly, almost incomprehensibly low. Precise measurements from the cosmic microwave background, refined through missions like WMAP and the Planck satellite, indicate that the universe sits essentially flat within about 0.4% of the exact critical density required to balance its own geometry. That total critical density, combining ordinary matter, dark matter, and dark energy together into one figure, works out to somewhere between 9.47 and 9.9 times 10 to the negative 27th power kilograms per cubic meter. In more relatable terms, roughly 5 to 6 hydrogen atoms worth of mass spread across every single cubic meter of the universe. But that figure includes everything: dark energy, dark matter, and ordinary matter combined. Ordinary, baryonic matter. The stuff that makes up stars, planets, dust, and every atom in your own body, constitutes only about 4.8 to 4.9% of that total. The remainder is cold, dark matter at roughly 26.8% and dark energy at roughly 68.3%. Filter out everything except the ordinary matter we can actually, in principle, touch and measure directly, and the density collapses further still, to a mere 0.3 atoms per cubic meter of space. This is a vacuum more perfect than anything humanity has ever managed to artificially produce in even our most advanced laboratory equipment. And while the interstellar medium within our own galaxy's disk is relatively dense, up to 1,000,000 times denser than the cosmic average, out in the true intergalactic medium, matter is close to genuinely, functionally absent. Here's a way to actually hold that number. Imagine scooping up a standard 1-liter water bottle's worth of average cosmic space, at random, from anywhere in the universe. On average, it would contain a mere 0.0003 atoms of ordinary matter. Run the statistics, and there is a 2,999 out of 3, 0.000 chance that any given randomly selected liter of the universe contains absolutely 0 atoms at all. Even scaling up to a full cubic meter, there remains a substantial chance, roughly 2 out of 3, that the volume holds nothing. And yet, remarkably, this same volume would not be entirely, philosophically empty of all physical phenomena. That same 1-liter bottle would still contain roughly 330,000 neutrinos. The ghostly, nearly massless particles left over from the universe's earliest moments, alongside ambient photons stretching all the way back to the Big Bang itself, an unknown scattering of dark matter particles, and the intrinsic vacuum energy that drives the entire expansion forward. There's one more twist worth including here, because it reframes even the sparse baryonic matter we've just described. Less than 10% of the universe's ordinary matter is actually locked up inside galaxies in the form of visible stars and gas, the vast majority. Up to 40% or more of all baryons that exist is believed to float freely in the intergalactic medium itself, in a highly ionized state astronomers call the warm-hot intergalactic medium, strung thinly along the very filaments of the cosmic web we discussed a moment ago. The space between galaxies isn't entirely devoid of matter. It's simply diluted to a degree that genuinely, mathematically defies human comprehension. Because the human mind has no native ability to process numbers like 93 billion light-years or 4.1 times 10 to the 32nd cubic light-years. Astronomers rely on aggressive physical scale models to make these distances conceptually graspable at all. Let's actually build one together. Shrink the entire Milky Way galaxy. Every one of its roughly 100 billion stars, its full 100, 0.000 light-year diameter, down to the size of a standard United States quarter, roughly 0.955 inches across. At this scale, Andromeda, sitting 2.5 million light-years away in reality, would be located approximately 24 inches, nearly 2 feet, from the quarter representing our own galaxy. The entire local group, in this tabletop model, becomes a small handful of coins and specks of dust scattered arbitrarily across a modest dining room table. Extend the same quarter-scale model outward to the larger structures we've discussed tonight, and the geography becomes genuinely alien. The Virgo Cluster, at its real distance of 54 million light-years, would sit about 43 feet away from our quarter. The Botez Void, that staggering 330 million light-year expanse of near-total emptiness, would stretch for approximately 260 feet, roughly the length of an entire city block, containing nothing but empty tabletop, save for a scattered few dozen coin-sized galaxies drifting somewhere within it. And the observable universe itself, at its full 93 billion light-year diameter, would span roughly 14.7 miles across. An entire sphere of space, more than 14 miles wide, with a single quarter representing our galaxy sitting somewhere inside it, another quarter 2 feet away representing Andromeda, and everything else reduced to scattered coins and dust motes strung along invisible, spiderweb thin filaments, separated by gaps the size of multiple football fields, containing nothing at all. This is the true geographic reality of the place we live in. Not a crowded metropolis of shoulder-to-shoulder galaxies. A vast, largely hollow sphere, 14 miles across on this model, containing a handful of coins. These staggering distances aren't merely geographic trivia. They impose absolute, genuinely inviolable limits on what any civilization, anywhere, biological or mechanical, could ever hope to accomplish. Limits enforced directly by the speed of light itself, the maximum possible speed of causality and information transfer anywhere in the universe. Even a hypothetical civilization capable of building a spacecraft that accelerates to a full 99.9% of the speed of light would find the intergalactic void a virtually insurmountable barrier. A journey to Andromeda, even at that near maximum velocity, would still take 2.5 million years to complete, from the perspective of anyone watching from a stationary point. Relativistic time dilation would compress the subjective experience of time for the crew aboard such a ship. But the civilization they left behind would rise and fall and be forgotten, continents would drift, and entire species would evolve and go extinct, long before that spacecraft ever arrived anywhere. Communication fares no better. If an advanced civilization residing somewhere within the Virgo Cluster transmitted a powerful radio signal directly at the Milky Way, that signal would require 54 million years just to cross the gap. If we detected such a signal today, it would mean it was sent shortly after the extinction of the dinosaurs here on Earth. Any reply we sent back would take another 54 million years to arrive. Intergalactic communication, under these constraints, isn't really communication at all. It's an exercise in cosmic archaeology, a monologue exchanged across geological time, structurally incapable of ever becoming an actual conversation. And here is the detail that makes everything we've covered tonight considerably worse, rather than simply large and fixed. These distances are not static. The universe is actively expanding, quantified by the Hubble constant, measured at roughly 67.4 kilometers per second per megaparsec. And that expansion is accelerating, driven by the dominant presence of dark energy, which accounts for 68.3% of the universe's total energy budget. Because the fabric of space itself is stretching, galaxies sufficiently far apart are receding from one another at velocities that exceed the speed of light. This doesn't violate relativity. The galaxies aren't moving through space faster than light. Space itself, the medium between them, is simply accumulating faster than any photon could ever hope to cross it. This produces a strict cosmological horizon. Any galaxy located beyond that horizon is fundamentally, permanently unreachable and unobservable, because its light will never manage to cross the ever-widening gulf of space separating us. And as dark energy continues accelerating the expansion, more and more galaxies are pushed beyond that boundary, permanently, with every year that passes. Hundreds of billions of years from now, the night sky will have genuinely, measurably emptied out. The cosmic web itself will be torn apart by the relentless stretching and every locally bound cluster, including our own eventual merger with Andromeda, will become an isolated island, surrounded by voids expanding faster than light in every direction. Any civilization born into that distant future era will have absolutely no observational evidence that a broader universe, or a cosmic web, or any of the structure we've spent tonight exploring, ever existed at all. They will look up, gather every scrap of evidence available to them, and rationally, correctly, given what they can see, conclude that their own single, isolated galaxy constitutes the entire universe. There's something worth sitting with directly, now that we've walked through the true architecture of the space between galaxies. The universe, examined honestly, is fundamentally defined by its emptiness. The stars, the planets, the galaxies that command every astronomer's attention are, in the most literal sense, incidental. Hypercompressed impurities floating in an otherwise pristine vacuum. Baryonic matter accounts for less than 5% of the universe's total mass energy budget, and of that already small fraction, only a microscopic sliver has ever managed to collapse into the glowing islands we call galaxies at all. And yet it is precisely this emptiness that allows any structure to exist in the first place. If the universe were perfectly dense, uniformly packed with matter everywhere, the resulting gravitational forces would have caused everything to collapse immediately back into a single, undifferentiated singularity the instant it formed. The vast voids like Bootes and the millions of light years separating galaxies like our own from Andromeda aren't a flaw or an absence or a disappointing gap in an otherwise complete picture. They function as the stabilizing breathing room of the entire cosmos, the physical canvas on which the cosmic web is painted, providing the dimensional framework that structure itself actually requires in order to exist at all. The psychological discomfort so many people feel when they first confront these numbers stems from a deeply, understandably local perspective. We evolved on a densely packed planetary body, surrounded by an atmosphere, by oceans, by billions of other living things. To a mind shaped by that environment, emptiness reads as absence, as something close to non-existence. But at a cosmological scale, the void is not nothing. It is an active physical entity in its own right, rippling with quantum fluctuations, humming with a constant traffic of neutrinos, stretching continuously under the persistent, patient influence of dark energy. And there's a final thread worth holding on to before we close. The vast distances separating galaxies highlight the profound physical isolation of any single star system, anywhere. But they also point towards something considerably warmer. Every galaxy within the full 93 billion light-year expanse of the observable universe is linked by the same shared gravitational legacy of the Big Bang, connected invisibly by filaments of dark matter that trace their structural lineage all the way back to the very first quantum vibrations of time itself. Separated by millions upon millions of light-years of silent, atom-starved void, every single structure in the entire universe is still, in a very real and physical sense, woven into the same vast, interconnected cosmic web. Picture it, one last time, before we close tonight. Somewhere out there, on a scale we can only truly grasp by shrinking it down to something we could hold in our own two hands, our entire galaxy. Every star you have ever wished upon, every planet, every living thing that has ever drawn breath, is a single coin resting quietly on an otherwise empty table. 2 feet away sits another coin. Andromeda, close enough, relatively speaking, to eventually merge with our own in 4.5 billion years, and yet still separated from us by a gap that light itself needs 2.5 million years to cross. 43 feet away, the Virgo Cluster, a scattering of 1,000 smaller coins. 260 feet away, in some other direction, an entire city block's worth of table, completely bare, holding nothing but a scattered few dozen coins lost somewhere in that vast, empty stretch. The Bootes void, where a civilization born in the wrong place might have spent its entire history believing itself utterly alone in existence. And the full table itself, 14.5 miles across, in every direction, holding, in total, perhaps 2 trillion coins, scattered thin along invisible threads, separated everywhere by gaps the size of entire towns. This is the true shape of the place you live in. Not the crowded, glittering metropolis the deep-field photographs seem to promise. A vast, echoing hollowness, patient and ancient, holding within it a scattering of glowing islands, one of which, impossibly, improbably, managed to produce something capable of measuring the emptiness surrounding it and calling it beautiful. We are a coin on an almost entirely empty table, and we are, somehow, the part of that table that noticed. Tonight we explored the true distance between galaxies, and what we found was not a single number, but an entire architecture of emptiness, considerably more extreme than the crowded deep-field photographs ever let on. We found that the famous images of thousands of shoulder-to-shoulder galaxies are a profound optical illusion, a flattened cross-section of billions of years of cosmic depth, mistaken by the human eye for genuine proximity. We found a real paradox in the mathematics of scale. Individual stars separated from their neighbours, by a factor of tens of millions relative to their own size, while entire galaxies, relatively speaking, sit only about 25 diameters apart. A closeness that still translates into a 2.5 million year journey at the speed of light to reach our very nearest major neighbor. We found an observable universe considerably larger than simple intuition suggests, a cosmic web of filaments and nodes stretching across the entire 93 billion light-year span of everything we can see, and a supervoid so vast and so profoundly empty that a civilization born inside it might never have known other galaxies existed at all. We found that the actual density of intergalactic space amounts to a mere 0.3 atoms per cubic meter, a vacuum more perfect than anything ever produced in any laboratory on Earth. And we found, when we shrank the entire observable universe down to the size of a scattering of coins on a 14-mile table, just how staggeringly hollow the true architecture of the cosmos actually is. And we found that this emptiness isn't a flaw in the universe's design. It's the very thing that makes structure possible at all. The breathing room without which nothing could have ever collapsed into a star, a galaxy, or a mind capable of measuring the distance between them. Sleep well tonight, knowing that the light reaching your eyes from the night sky has crossed gulfs of near-total nothingness to arrive, and that you exist, against every overwhelming statistical odds, as a rare and glowing exception to the vast, patient dark that fills nearly everything else. Good night, and rest well under a sky far emptier and far more remarkable than it has ever appeared to be.